Everyone, today we're going to learn a new type of reaction called oxidation reduction reactions. So what exactly is an oxidation reduction reaction? An oxidation reduction reaction is a reaction in which electrons are transferred from one reactant to another. We often call these redox reactions for short. Red stands for reduction and ox stands for oxidation. Now, one of the most familiar redox reactions is actually a corrosion of a metal. And if you aren't for sure what a corrosion is, it's the conversion of a metal and turning it into a metal compound. For example, green coating that forms on copper roofs. Copper is typically this brownish color, but over time you might see it turn green or get this green coating. That is going to be a redox reaction. A good example of this in real life is the Statue of Liberty. It's technically made out of copper and used to be a brownish color, but over time, it has had redox reactions happen to it that has turned it green. Iron rusting is another example. You have an iron, which is a metal, and it's turning into the metal compound of rust, or in other words, iron 3 oxide. So, what does oxidation and reduction stand for? Oxidation is the loss of electrons. So, if you're losing a negative charge, you're becoming more positive. Reduction is gaining of electrons. So, if you're gaining a negative charge, you're becoming more negative. My biology and college professor always gave me the acronym LEO, the lion goes grr. And Leo is like an astronomical sign. It stands for losing electrons, oxidized, and Gur stands for gaining electrons, reduced. Now, one thing to understand about redox reaction is whenever one reactant loses electrons or is oxidized, that means the other reactant has to gain them or they're going to be reduced. Oxidation has to be accompanied by reduction, so you can't have one without the other. Now, a reaction between a metal and either an acid or a metal salt is called a single displacement reaction. What happens generally is the ion in solution is displaced through oxidation of an element. Our general reaction is A plus Bx yields Ax plus B. A and B are my single elements. If it's attached to X, these two are compounds. Typically, element A is going to take the place of element B and kick B out by itself. Down here, we have two examples. Here, my zinc is going to come in and take the place of hydrogen. Now, hydrogen is going to be by itself and zinc will be in the compound. Manganese, in the second example, will come in and take the place of lead. So manganese is now with nitrate, and this kicks lead out to be by itself. So how do we know if redox reactions are going to happen? Well, it's all determined by something called an activity series. An activity series is a list of metals in order of decreasing ease of oxidation. So what exactly does that mean? Well, metals at the top of the table are going to be easily oxidized. In other words, they're going to want to form compounds, everything at the top. We call these active metals. So these are generally things in group 1A and 2A of the periodic table. Elements towards the bottom of this activity series are pretty stable, and so they don't want to form compounds. They like to be free metals. Sometimes we call these noble metals. Now, any metal on the list can be oxidized by elements below it. So before we go into an example, let's actually look at the activity series. This is a chart that I will print off for you for your test. Note that all the metals towards the top are reactive and they want to be in a compound. So the tops want to be in a compound. The bottom don't need to be in the compound as much. So a couple things with this chart. I like it because if the element, the metal is by itself, it will be written as what's on the left. So if aluminum's by itself, it's aluminum as a solid. What's on the right is what the charge of it will be if it's in a compound. So for example, if you're making a calcium chloride, we know that when it forms that compound, calcium will have a 2+ charge, and zinc will have a 2+ charge. Chromium will have a 3+. Let's get a practice using this. So will an aqueous solution of iron 2 chloride oxidize magnesium metal? In other words, you need to ask yourself, is iron below magnesium? Because in order to oxidize, it needs to be below it. So you need to go to your table and you need to find iron. So here's iron. And you need to see, is it below magnesium? Well, here's magnesium. Yes, iron is below it. So, will iron oxidize magnesium? Yes. Typically, you want the metal highest on the table to be in the compound. So here, magnesium is highest in the table. That means this reaction will happen because magnesium wants to take the place and be in the compound. Let's look at a few more examples. Which of the following metals will be oxidized by lead nitrate? So in other words, you need to ask yourself, is lead, Pb, below any of these others? So we have zinc, copper, and iron. So I have zinc, copper, and iron. And we all want to compare it to lead. So let's find lead. So we need to ask ourselves, is lead below zinc? Here it is. So yes, this one will be oxidized. This will want to be in the compound. For copper, is lead, let's do zinc. Copper, is lead below copper? Well, here's copper, and the answer is lead's not below it. No. So this will not be oxidized. The last one, iron, is lead below iron? The answer is yes. So what that means is anything that is above lead will actually have a redox reaction happen. If copper and lead nitrate reacted together, there would be no reaction since copper couldn't be oxidized. So we're going to learn how to write ionic and net ionic equations. And first, you have to figure out, can the reaction even occur in the first place? So here, whichever one is highest on the table wants to be in the compound. So here we need to see, is hydrogen below aluminum? So if we look, is hydrogen below aluminum? And so here's aluminum. Hydrogen is below it, so yes, this reaction will take place. The way it then works is I need to figure out what are my products. Well, typically what happens is hydrogen is going to be kicked out. So you have to figure out what is hydrogen when it's by itself. We're going to look at this table. When hydrogen is by itself, it's going to be written as H2 as a gas. So I'm going to write it by itself, H2 as a gas. Plus, then we have to figure out, well, what about aluminum and bromine? If you look at this table, aluminum, when it's in a compound, has a 3+ charge. So here, aluminum has a 3+ charge. Bromine has a -1. When you cross it, you get AlBr3. Then it comes back to your solubility table. Is this soluble? Well, bromine is soluble, and this is not one of the exceptions. So bromine stays aqueous. Then you know this can happen. We need to write the ionic and the net ionic equations. Well, in order to do this, we need to balance it. To balance it correctly, you're going to write 3 aluminum, 6 hydrobromic acid, 2 aluminum bromide, and 3 hydrogen gas. Remember, you can only dissociate strong aqueous solutions. So here, this one is not aqueous, so it stays as is. When we go to the next one, this one's aqueous, and then it's an acid, so we have to check. Is it part of my strong acid list? Yes. So you can dissociate it into 6H plus ions plus 6Br negative ions yields. When you look at this one, hydrogen is in a gas, so it's not aqueous, so I have to keep it as is. That's supposed to say gas. And then you look at the last one, aluminum bromide. It's aqueous and strong because aluminum is a metal. So 2 aluminum, and remember, aluminum's a 3 plus charge, plus here we have this 3 doesn't belong on bromine, so 6 bromine negative AQ. Then you cancel what is exactly the same on both sides. So my 6 bromine cancel, but my aluminum can't because this one has a charge and this aluminum doesn't. So we write it as is. So when you finish writing this out, this is what you get for the net. So let's look at this one. First, we have to figure out, is the reaction going to occur? So that means, is lead below copper? So if we look at this table, here's my lead and here is my copper. Lead is not below copper. So you can tell straight from the start that this will not happen. No reaction. Because Pb is not below copper. And this is our last one that we're going to work through. Here, will the following reaction occur? So, actually, I want you to try this one on your own. When you get done, I want you to actually bring it up to me and check it. And if you have it, I will give you guys your worksheet, and I hope you guys have a great day. Let me know if you have any questions.